tech stuff going before it fries. Okay, so real quick, all these guys have been having this, so at home, if you're recording this, just go ahead and pause the video and write this down. What we're looking at today is the standard deviation. So I'm going to come and go over the definition real quick and then do that kind of stuff. This is the word use. I was looking at that and it looks awful. Okay, so if we use a least squares regression line to predict values of response variable y from an explanatory variable x, the standard deviation of the residuals is given by s is equal to the sum of the residuals squared over n minus 2 is equal to, and then it's also, I put it as the formula, okay? Now, do we need time or can I go on? Looks like we need time, so we're going to pause it here because I'm lazy. All right, yn minus 2, all right? So I'm going to answer the question with a question, all right? So how many points does it take to make a line? And you would all answer 2, okay? So what we're looking at with the standard deviation is the variance. How are things changing, okay? So if we just have 2 points, is there going to be any real change between those 2 points? No, there cannot be 2, because if you have 2 observations, right? 2 observations, you can't see any variance between you're not seeing the variance between those 2 points. You need a minimum of 3 points, okay? So we need a minimum of 3 points. Minimum of 3 points, okay, to see any variance. Now, you can see with 2 points, right? You can see an association, right? You can see whether it's positive, you can see that it's negative, and you can see how weak that positive negative line is going to be, okay? So the association is fine between 2 points, but you won't be able to see any variation unless you have 3 points, okay? Now, if you only have 3 points of data, that's horrible, first of all, but it allows you to start seeing a little bit of prediction. If you did the applet yesterday, I don't know if anybody saw the video yesterday, we did this little thing with the computer that the book set up that you can actually go on and make different scatter plots, and you can change the variance and everything like that. It's pretty neat. Just saying. Just putting a plug in. Don't forget to hit like, subscribe, so I can start making some money. All right, this is our typical, okay, distance of the data points from the mean. So that was our definition for our standard deviation. How far are we from the typical distance from the mean? All right. Now, we're actually using a linear squares regression line. Okay. So the S for us is actually looking at the typical distance from the regression line. Okay, so we're looking at what that typical distance is going to be for our all our residuals. Okay, so that's all the S does. So it's very similar to the standard deviation that we've done, which tells us how far away from the mean we are. So the standard deviation of our residuals is going to tell us our typical distance from our regression line. Okay, so that's going to tell us, you can kind of look at it as our plus minus type of a thing. Okay. Okay. So anything over, we're going to give you an example. Don't freak out on me. Any questions you want to go over from what we've seen here? Anything from the peanut gallery? That's you three. Thanks, Barry. Okay, so another way to see how good our data is with the coefficient of determination. That's your R squared. All right. Now, what I'm going to do is I'm going to give you the formula, and then we're going to give you the definition, and then I'm going to give you how it needs to be written up. Okay. So a lot of things to be given to you. So R squared is equal to 1 minus the sum of the residuals squared over the sum of minus yi, well, y hat, y hat squared. Wait, that's, yep, I was right the first time. yi minus y bar squared. Yes. Okay. So the coefficient of determination, so I'm just going to put r squared, still on there, sweet, okay, is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. Okay, so I'm going to pause it here. Everybody write that down and then we'll talk about it. Is this part right here, and unfreeze it. This part right here tells us what is not explained by the graph or the linear regression line. Okay, so when we subtract it from 1, that percent tells us what is explained by the equation. Okay, and so the closer we are to, say, 100%, the stronger or better off our equation is. Okay, so it's between 0 and 0.99. Okay, and we're going to be looking at how strong that data set's going to be. Okay, so we're asked to state it kind of as this little statement here. Okay, the percent, whatever r squared is, of the variation, and when I say the y variable, right, kind of think about yesterday's soda when we were talking about time tapped and the milliliters left. Okay, so this would be the milliliters left is accounted for by the linear model relating milliliters left in the soda to the time the soda cans were tapped. So when it says the x variable, it's actually just talking about what those x units are and what they're looking for. Okay, so this is going to be our problem to help solidify some of the standard deviation and the uh, coefficient of determination. Okay, so this is going back to the first one. The first things we did was sprint and long jump and did the scatter plot. Okay, so the first thing I want you to do, number one, you're going to make a scatter plot. Even though we've done it, you're going to do it again because you're going to need the data. You're going to find the least squares regression line. You're going to state the correlation coefficient. Which variable is that? What's the correlation coefficient? Anybody? R. Okay. You need to give the association. Okay. And you can't just say that there is an association. You have to tell me whether it's positive or negative or no correlation, okay? 5, we're going to create this residual list, which we did yesterday. 6, we're going to make a residual plot, which we did again yesterday. A, using your residual plot, does a linear model make sense? Why or why not? 7, calculate and interpret the residual for Christian, who had a sprint time of 7.25 and a long jump of 110 inches. Okay. And then 8, we're going to interpret S. 9, you're going to interpret R squared. Okay. What I've done is just made a rough sketch of my scatter plot from my calculator. Make sure we're not putting on calculator as our answer. We need to do a visual representation of what we've seen and what we've done. Okay. So that takes care of number 1. So we've stated our regression line. We've done our correlation coefficient. We stated that it's a strong negative correlation. We had a question about putting the best line of fit in, or the linear regression line, excuse me. So I put that in as best I could with my calculator, and then I just wrote the equation up there. The other thing I need to do is make sure that I put my arrows on there. Okay. Okay. Okay, so we made a residual plot. So this is going to be our X value, which was sprint time. And then right here is our residuals. If you need help graphing your residuals, please go watch yesterday's video or come in and we can work one-on-one, make sure that you can do that residual plot. Now, because there's no clear pattern, there's no parabola, then the question is, can we do a linear, does a linear model make sense? So the answer to the A is yes, because there is no pattern and no parabola. I probably misspelled that. Okay. So for number 7, we used our linear regression line. We put in 7.25 for our X. We predict with that sprint time, he should be able to jump 83.0775 inches. Okay. But we observed that he did 110 inches. So the residual is 26.9225. So his residual was 26 above our prediction, or nearly 27 of what we expect him to do. Okay. All right. So what we're looking at is we're doing this the standard deviation. We want to know where to find our residual squared. So if you go to calculate one variable statistics, instead of list 1, we're going to put list 3 down here. All right. And then we're going to calculate. We know that X represents our residuals because that's what list 3 is. So this is the sum of the residuals squared. So that's 4966.36. The 12 came from the fact that there are 12 terms. So if you put that in your calculator, you should get about 22.38 inches. Okay? So I'm going to pause it and then, because I'm running, I only have. So when we're recording or stating our conclusion using our standard deviation, we'd state something like, when using the least squares regression line with X equaling sprint time in seconds and Y equal long jump distance in inches, we'll be typically off by about 22.38 inches. And I don't care if you repeat this over and over again for all the questions, that format, it's the easiest thing to do. Okay? All right, so R squared, we just used our linear regression equation from our calculator. It gave us that value there. It says we got 0.70468. We have 78.47 of the variation in long jump distance is accounted for by the linear relating model long jump distance to the sprint time. So what that means is that we can account for 70% of the time, which really isn't that bad. I would use it. If it gets closer to 0, I get more nervous. Okay?